We are going to solve this problem, most stones removed with the same row or column. LeetCode problem number 947. It's a very interesting problem, and there are multiple ways that this problem can be solved. In fact, I don't know why there are so many negative votes on this one. This makes for a very, very interesting problem. So let us see what the problem is asking us. We are on a 2D plane and we place n stones at some integer coordinate points. Okay. Each coordinate point may have at most one stone. Okay. So it feels like a graph thing. And on a graph there are obviously multiple coordinates, and each stone can be placed on one point and there cannot be multiple stones, right? A stone can be removed if it shares either the same row or the same column. Yeah, so I think this is an important line here. So if a stone has the same row and same column as another stone, then it can be removed from there. Given an array stones of length n, where stones I is equal to xi and yj represents the stone of ith stone, return the largest possible number of stones that can be removed. So we are interested in the largest possible number here. So let us try and understand through a graphical representation what the question is trying to ask us. So for your reference, I have created a couple of graph representation here. Let us see. This is the same graph representation as given in the LeetCode example. So this is the list of stones that we are given with, and we have plotted these numbers on a graph. So you can think of each of these stones as a node in the graph, right? So this is 0 0, and then this one is 0 1 1 0, and then 1 2 1 2 would be this one, 1 2, and then 2 1. So 2 1 would be this one, and 2 2. And a node, two nodes would have a line in between them, or you can say an edge between them if they share the same coordinate. So see, this one and this one, they share their x coordinate. It is 0 for both of them. And while this one and this one, they share their y coordinate. That's why there is an edge between them. So now the question was saying we can remove a stone if and only if there is another stone sharing the same x coordinate or y coordinate with them, and that is still unmoved or not removed. So let us see what we can do here. Let us start with let's say this one. So I'll pick red color to show that this has been removed. So I have removed this one because it shares x coordinate and y coordinate with two stones which are not removed yet. So I've removed this one. Then let's go to this one because this shares with this particular one. So we can remove this. Let's go to this one. This shares y coordinate with this one. So we can remove this. Then this one, this shares x coordinate. So we remove this. Then come to this one because this shares y coordinate with this one. So remove this. And in the end, we are left with just one stone, right? So out of 5 stones, we are left with only one stone. Can you see what is happening here? So all of these stones were connected to each other. And if you think about it in terms of a connected graph, in a connected graph, we are left with only one node. The rest of the nodes have been removed. I think the next example should clarify this. So over here, this particular node is not sharing any x or y coordinates with the other one. So this is not connected. Otherwise, let me use a different pen. Yeah. So this is connected, this is connected, this is connected, and this is connected. Not this one. So how do we remove something? Similarly, just like the previous question. So first of all, we remove this one, and then we go to this one because this is sharing y coordinate, x coordinate with this one. So we can remove it, we can remove it, and then we are left with this one. We can't remove the middle one because this is not sharing any coordinate with any other stone. So we are left with two stones. And again, notice that this was a connected graph. So out of each graph, we are left with only one stone. In this particular graph, there was only one stone, so we are left with one. So basically, the question reduces to this problem statement that first you need to count the number of connected graphs. Once we know, or connected components, connected graphs, whatever you like to say. Once we know the number of connected graphs, then we are left with only one stone at the end. And that is all the question is all about. The question is asking only this thing. And also please note that the question was asking about the largest number of nodes. So in another combination, this could be possible that we removed one stone, and there was because that was the only connecting stone between two other stones, so we could not remove other stones. So as a result, we were left with more stones. Because we are interested in removing as many stones as possible, this is the best strategy that we can come up with. So essentially, the problem has reduced to finding connected components in this set. So now finding connected components has two ways of doing it. One of the possible way is to go with a DFS based solution. So we start a DFS search from one node, and then we go to the next node that it is connected with, then next node, and then we backtrack to the same node, and then we go to another branch that it is sharing a connection with. The second possible way that I am going to try here is union find. Union find is another very interesting data structure, and if you haven't used union find yet, I would highly recommend understanding union find before attempting this question. It's a wonderful data structure, and it is going to be useful in solving a lot of coding problems, interview problems. Let us see how we can use union find. So before I start with the implementation, I'll just quickly write down the code for union find. That could be a template code, so you could just copy and paste it from somewhere else. So I'll create a class union find. And then I'll create a constructor method which accepts length. This dot parent, this is going to be an array. And each of the element of this array is going to point to itself. So it returns I, and then rank as well. This helps in getting a better time complexity. So fill 1. Then let's implement the union method. So union between two numbers, let's say x and y. Before that, I would implement find method, find x. So if this dot parent of x is equal to x itself, then just return x else this dot parent of x is going to recursively call itself with this dot parent x and then return this dot parent x. Similarly, for union, we'll find parent of x using this, then parent of y using this dot find y, and then if parent of x and parent of y are the same, that means x and y are already part of the same union set, so there is no requirement of joining them again, so we just return parent x. Then if parent x and parent y are not equal, then we'll need to look at their rank. So this dot rank of parent x, if the rank of parent x is less than this dot rank of parent y, this means parent y will become parent x's parent. So this dot parent of parent x is going to be parent y, and we return parent y here. Else if this dot rank of parent y is less than this dot rank of parent x, parent x, then the same thing happens. Parent of parent y is assigned as parent x and return parent x. Else, now this is the condition where both parent x and parent y have the same rank. So in that case we can make anyone as a parent of the other one, but we need to make sure that their rank is incremented. Parent x, so this dot rank of parent x increases by 1, and then in the end just return parent x. So we are done with our union find implementation. That was quick. Now let's come to making unions out of these stones. So first of all, I'll initialize union find and stones dot length. Then we have created our union structure. So now let's go through all the stones. So y is equal to 1 and I plus 1, and y should be less than stones dot length y plus plus. So over here essentially what we are trying to do is we are trying to check each stone with every other stone whether there is a common connection between them. And what is that common connection? Is there do they share one of the coordinates, right? So we are checking if stones I has stone I and stone, let me make it j just to make it simpler, j and j. So if both the stones share their x coordinate, or if both the stones share their y coordinate, which is going to be 1, j1, in that case we are going to create a union between them. So union find dot union of I and j, both the stones, right? Now in order to we are very close to the result here. So now we must be having the number of groups that we have formed. So as per the initial explanation that I gave, the return value would be the total number of graphs that are present in this minus total number of stones present in this minus the number of graphs individually. So that is going to be stones dot length minus number of groups, count groups. And where is that count? We could quickly implement this method, get count, and the count would be equal to we'll go through the array, and then that count is equal to 0. From that, this dot parent dot length, and we'll look for the parent of every node and put it in a frequency map. Frequency map of I, not I, this dot find I is going to be, in case if it is not defined, then initialize it if it is not initialized yet. Otherwise frequency map should be by 1. Actually we just had to create a set, but even this is fine. And then finally we need to return the number of keys. So return frequency map length. So this would be union find dot get count. I think this looks fine. Let me try and run it. Yep, passes the test. Passes. Submit. Yep, this looks good. Okay, so while this solution works well, I feel that there is a possibility of improving further up. Why? See, there are 2 for loops here, which means because of these nested for loops, the time complexity of this solution is going to be n square, order of m square, and that's not good. We should somehow get it in linear time, and there is a possible way, and let me tell you how. So coming back to our initial discussion that we did here, what if there was a way to change the way we are depicting these this graph? So at this point in time, what we have done is we are showing our points as nodes in this graph. But I want to say, what if on the place of showing it, considering these points as nodes in our graph, what if we consider something else as nodes, and that something else is going to be x coordinate or y coordinate? So for example, in this case, think about it. We have 0, 1, 2. These are the values of y, and 0, 1, 2. These are the values of x. So I am going to call it 3 or 6 different nodes, x1, x2, x3, y1, y2 and y3. Now let us see in what conditions these nodes are going to be connected to each other. So these nodes will be connected to each other if there exists a point on the 2D plane that has x and y as its coordinates. For example, so actually I wanted to do it x0, y0, x1, y1 and x2, y2. I hope that's okay. So or in fact, let me just quickly fix it so that there is no confusion later on. Yeah, so I wanted to 0, 1 and 2. 0, 1 and 2. So let us see. 0, 0. That means there is a connection between x0 and y0. 0, 1. 0 and 1. Then 1, 0. 1, 0. Then 1, 2. 1, 2. Then 2, 1. 2, 1. Then 2, 2. So 2, 2. So this is our modified graph from what we have here. What is the benefit that we get from it? Benefit you will get to see very soon, but we won't need to go into a nested loop is the direct benefit that you will see. So we make sets of x, sets of y, and then we connect x with y and y with x. And then finally we'll see we'll create unions out of these values. So let me quickly also show it for the next example. In this one we have x0, y0, x2, y0. So let me just make it for you. So x0, x1 and x2. Similarly y0, y1 and y2. Now x0 and y0 are connected, so x0 and y0, there is a edge between them. Then x2 and y0, so x2 and y0. Then we have x1, y1, so x1, y1. Then x0, y2, x0, y2. And then finally we have x2, y2. So there we go. Now looking at this graph, we can see that x0, y0, x2, y2, they are all connected to each other. So that is making one graph. While x1 and y1, this is making another graph. So there are two graphs in this, two graphs. And from our earlier discussion, you remember 1, 2, 3, 4, 5. So there are total 5 points. And we need to decrease 2 from it, and 3 is going to be our answer. So let us see how to implement this in the code. This is the code that we had already written. I'll need some small change in the union find code in order for this new function to work. So I'll just copy paste something that I've already written. There is not much difference between this code and what we had earlier. The only difference is that on the place of an array, I am going to take a hash here, and in the code for find, you see this place. So in case if we do not find an element which is already there in this union, then in that case we define it. So we add it to the parent element, and then we add its rank. And now we are no more counting the number of sets, number of disjoint sets at the runtime. We are marking it while we are finding and unioning things, right? And this is also a small change here. Sorry, this one. So we just decrease the count when we are unioning something. So with this code in place, let us get rid of this section. And now union find doesn't require a length to be defined in the beginning. So what do we do here? We loop over all our points. So let I is equal to 0, I is equal to less than stones dot length. I call it points, I call it stone at times. So stones dot length and then I plus plus. What is the x value here? Let x is equal to stones I 0, and then let y is equal to stones I then 1. So until this point everything should be clear, right? Now from our graph, if you remember, see, so we make nodes out of our x values and y values, right? So x0 becomes a different node, y0 becomes a different node. So how we could go ahead with it? These nodes could also become different sets in the union structure, and then we are going to make a union out of x and y value if there is a stone that has x and y as its coordinates, right? So over here we'll create a union out of x and y, but now the problem is x could have the same value as y, but we need to differentiate between x and y, right? Over there we were doing it like x0 and y0, so here as well we need to do something. We could potentially use a string as well, but another interesting trick over here could be on the place of writing it as y, what I could do is I could use bitwise negation. So by using bitwise negation, y gets a different value, and then we can do a union between them. So union find dot union, and I'll do x comma y, and this goes on for everything. I think this is quite interesting. This is surprising, but this is the only set of change that is needed, and let us see if it works. Yeah, it does. So I'll just submit it. Yep, it works. So with this small change, we have brought our time complexity from n square to order of n.